Now that we have analyzed the common emitter amplifier with resistance Re, and we have seen that when we have a discrete Re resistance at the emitter, it is better to use T model, because in this way you can see how this resistance is playing its role into the circuit, right? It is being seen at the input while looking at the base in series with Re, and is seen because it is at emitter, but it is seen at base 1 plus beta time, right? And this is the gain expression, let's say for GV naught, right? And the common emitter amplifier without Re, as analyzed previously, because of no emitter resistance, discrete emitter resistance at the base, we used pi model, right? For common emitter amplifier without Re, right? We use pi model, right? And for common emitter amplifier with Re, we use T model, right? Here Vn, right, is a part of V signal which is appearing at the base. Part of V signal appearing Vn at the base, right? And this Vi will be same because of the parallel resistances Rb and 1 plus beta time Re and Re, right? In contrast, here common emitter amplifier without Re, the input again is a part of V signal, right? Vn is a part of V signal, Rin divided by R signal plus Rn, right? Vn. And this Vn is same for the parallel resistances Rb and R pi, right? So Vn is equal to V pi. So that's why at that time we named this voltage, the part of V signal which is appearing at the base, at the input of the stage, as Vi. But this is V pi, but this is Vi as well, right? So the gain computations for these we already gone through and have found this relation, right? And this recently we have solved GV naught relation for common emitter amplifier with Re, found to be this. Here you can see the relations are same except this factor, and this factor is basically explaining, representing you that the part of Vi at the base of the transistor, of the stage, part of the Vi at the stage of the transistor, right? Here Vi is not further divided, right? But actually it is appearing the same to V pi because these two resistances are parallel. But here Vi is same for Rb and for 1 plus beta time Re plus Re. It means this Vi is developing across the series combination of these resistances, 1 plus beta time of the series resistance. Let's say, just for the sake that 1 plus beta can be multiplied with both of these, so still in series. So how much voltage will be appearing here is not Vi, it's part of Vi. It means Vi will be divided into two parts, one is here, one is here. Yes, here it would be Vi, Vi, but part of Vi is called VVE, part of Vi is called VRE, capital R, right? So VVE is a part of this, and it can be found by using voltage divider lines. V in here, VBE here, so VBE is equal to RE divided by RE plus R capital E into VI. That's what we have computed previously, right? So it means here VBE is equal to part of VI, whereas here VBE, you can name it VBE or V pi because of the pi model, is directly equal to VI, right? Whereas here, for example, if you want to write VI in correspondence to V signal, so this is the relation. But here VBE in correspondence to the V signal is same up to here, but this one is different than this one. Why? Because of this combination. Okay, let's go further. We are actually comparing the common emitter amplifiers with RE, without RE, to see what are the advantages of using RE or not using RE, and what are the disadvantages of using RE or not using RE. So with RE we have this gain relation, without RE we have this gain relation. All the things are same except this relation, right? Because of the presence of this resistance, it is now coming in series with this one, right? So VBE is equal to RE divided by RE plus RE into VI, whereas here VBE is equal to V pi is VI and VI is this one. This multiplied by V signal, which is down here. And here VI is equal to Rn divided by Rn plus R signal into V signal. This, and VI, if we put instead of VBE, then VI and VB having this relation, right? Same as per the previous slide, right? So then what is the difference? What difference can we see here? And what difference we have seen while computing the gains? Remember, the common emitter amplifier without RE we have done for in the topic of discrete amplifiers without RE, right? That has gains in hundreds, but now with RE, we in previous lecture, the with RE common emitter amplifier has gains in units, not in hundreds. It means gain is reducing, and now we are actually going to see computationally with expressions how it is happening. So here we can see Vi is equal to V pi is equal to VBE. It means the part of V signal out of Rin and R signal is Vi and it is appearing directly to VBE. Here part of V signal about Rn, R signal and Rn is becoming Vi, but it is not VBE. The VBE will be further actually part of this Vi. How much part? This much fraction part, right? So let's simplify this to have some knowing relation. If I throw this RE towards the denominator of this RE plus RE, we got this and break the axiom, and this become 1. We know that RE is equal to alpha by GM, right? VT by IE or alpha by GM. So we can put RE is equal to alpha by GM. So GM RE divided by alpha. So is this will become 1. This will become GM RE by alpha, and alpha is is nearly equal to 1.996 or 0.99. So we can neglect it to or approximate it to 1. So this is what we have achieved. It means a common emitter amplifier with RE and a common emitter amplifier, sorry, with RE is this one, and without RE. So common emitter amplifier without RE, V in the signal at the base to emitter will be equal to V in. Whereas here VBE is not equal to VI, but it's a part of this. How much part? This much part. It means if you want to have same VBE here, and here. Then you have to make VI for common emitter amplifier with RE this much high, so that you can apply same VBE to with RE amplifier and without RE common emitter amplifier. I hope you got my point. Thus, for the same VBE here and here, the signal at the input terminal of which one? This common emitter amplifier with RE. With RE amplifier, you need to make this VI this much higher, so that two things will cancel out and this will become equal to this one. Then you are actually applying the same thing here. Otherwise, your same VI is not applying at the VBE for RE, because of some voltages are being distributed at the discrete resistance R, right? So let's further summarize it in the presence of this and by recalling the figures we have presented in the previous slides. To summarize, including a resistance in the emitter here, common emitter amplifier results in the following characteristics. So disadvantage has been seen that it actually reduces the gain by this much, right? Why? Because it can see only this part of VI, not the whole VI, right? So let's see. The input resistance is increased by the factor 1 plus GMRE. This is the advantage. You want your stage to be having input resistance very high. So now your resistance is very high. Whereas in case of common emitter without RE was what? RB parallel to R pi. And usually this RB is very high, so it's actually R pi, and R pi is equal to 1 plus beta RE, only 1 plus beta RE, small RE, right? But here it's not only RE, it's 1 plus GM into RE, right? The voltage gain is reduced by the factor this is the disadvantage I have told you, right? Because this much signal is being appearing at the base to emitter is being appearing less at base to emitter as compared to without R. So it means whatever voltage is appearing, it is actually amplified. So low signal is appearing, lower will be the gain. The overall voltage gain is less dependent on the value of beta. This is the advantage. You want your amplifier to be independent of beta. The high frequency response is significantly improved. We shall see this later. So all of these factors except the gain reduction is the disadvantage. Other are very good things to be having in a common emitter amplifier. With the exception of the gain reduction, only this part. These characteristics, all of these other characteristics, represent performance improvements, right? So what we can do to have gain, also improved gains, besides having all these advantages as well. So we have another amplifier here. You can see we have RE, but it is bypassed. And when you find the DC equivalent circuit of this one, this capacitor will be open circuited. Yield this one, you will get this DC circuit, right? It means RE is present in DC. But when you find the AC equivalent circuit, that what circuit this signal is seeing, you can see you will short your capacitors, short, and it means you are shorting your emitter to ground directly. So current will try to go through this one, not through a resistance, right? And which current? Because this capacitor is short circuited for AC signals, it means only AC signal will try to go from here. So it means your AC equivalent circuit of this amplifier will not be having RE. So in this way, your amplifier having good independent of beta relation, and your gain is improved, right? Now this is not in the part of the AC signal, so your gain is improved.